Hello guys, welcome back to ptet.chemistry channel. So in this lecture tutorial, I'll continue this year 9 or the 14 to 16 years old O-level or the IGCSE curriculum. This is a continuation of the mole and the Avogadro constant subtopic. Where in this next part of the tutorial video, I'll focus specifically on reacting masses, the idea of limiting reactant as well as excess reactant. So together with limiting is to do with excess reactant. So limiting is something that is used up completely. Excess basically is something that is present in excess, hence it's not used up completely. And then we're going to be talking that in terms of the volume of gases, in terms of volume of solutions, and even reacting masses as well, and these things, volume of solution and concentration of solutions can be interchangeably used in gram per dm cube as well as mole per dm cube, and that's why they say interconversion between cm cube and dm cube, where 1 dm cube is equal to 1000 cm cube, therefore 1 cm cube is equal to 1 over 1000 dm cube, where we need to convert any cm cube to dm cube in order to multiply by the concentrations, especially the molar concentration expressed in mole per dm cube. In the previous lecture tutorials on solution chemistry, specifically on mole calculations involving solutions, I talk about the interconversion from mole per dm cube and gram per dm cube. The relationship from getting this into this is simply this one divided by the molar mass, which is mr, or relative atomic mass, which is ar in gram per mole, and the unit matches out, so you can watch that lecture tutorial if you had missed that particular lesson. Now, specifically on this idea of excess and limiting reactant, so it's very rare that they'll ask you to define it, but definition is the very first thing that we should know if we want to describe something to other people. Before we can use the term, we've got to understand what it means. Stoichiometric amount basically refer to based on balance equation. So based on your equation that is balance, so that is in terms of mole. So we got to think about excess reagent, excess reactants. They mean the same thing. So they are not completely used up. They are not completely used up, and that is the most important thing. Since they are not completely used up, you can never ever use the mole or the amount of excess reactant in your mole calculation. For mole calculation, because they will not tell you how much product you get, because not all of them are completely used up, not all the excess reactant is completely reacted. On the other hand, limiting reactant is what you must use in order to do your mole calculations to find out how much product is obtained, because the limiting reactant is completely used up, is completely reacted, none of it is left at the end of the reaction. And that is the one that will determine the yield of the reaction. So I've provided a couple of examples here, so it's better exemplified. The concepts are better exemplified through seeing it from the lenses of examples. So here we have a balance equation. This is iron 3 oxide. So just to remind you, of course you don't need to be reminded, because these are things which you should know very well already from a couple of lecture tutorials ago. When we do this cross multiply, we never cross multiply the charges, we cross multiply the value, because the value is the LCM, is the lowest common multiple, which is 6. So plus 3 require 2 multiples, two of these, meaning 2 iron 3 plus, so it's Fe3 plus and Fe3 plus, and you have 2 or 2 minus, because we never cross multiply the ions, we never cross multiply the charges, we cross multiply the numbers, because that's what we call lowest common multiple, which is your primary school mathematics. So altogether you have 2 iron 3 plus and 3 oxide, meaning 3 or 2 minus. Iron 3 oxide with chlorine and potassium hydroxide, K plus and OH minus. Hope you can see here, this is going to be K plus 2 of them, because they are 2 K plus, which leave the Fe of 4 being 2 minus. Very important that you can work out the anion based on what you know about the cation itself. This is K plus Cl minus, and this is H2O, which is not ionic, but H2O is a simple covalent molecule with a simple molecular structure. Now we have these masses. So this is a solid, because, well, it's a giant ionic structure, metal and non-metal. And you're gonna add it to this solution because it's aqueous, because it's dissolved in water. It has concentration of 4.00 mole of these per 1 dm cube of water, and you have this much volume. So the amount in moles, so N, which is the shorthand notation for mole, the mole of Fe2O3 is mass over the MR. I should work out the MR or Fe2O3 on the side just while I'm at it. So go straight to the periodic table, and iron is 56, the MR, so it's 56 times 2 plus 16 times 3. I want to move this somewhere so that I don't run out of space. What does this give me? 56 times 2 plus 16 times 3, that give me 160. Don't forget the unit of MR is actually gram per mole. So the mass is this 2 grams, so 2.00 divided by 160 onto your calculator, and I get 0.0125 mole. So I guess I should be able to, show the MR as well, which is probably why it's 2 marks there. 1 mark for the MR, and the second mark is for the calculation of that. Fe2O3. I will want to label everything and not just whatever working that you want to put in, because things have no meaning at all unless you label your stuff, and things have no meaning at all unless you associate it with a unit. This is mole, so this is mole. By right, you should put in gram per mole, but it's self-explanatory just as long as you have it on top of your head. Okay. Now you want the mole of the KOH. So the KOH is a solution, as I mentioned just now. It's dissolved KOH in water, so it's a mixture. So concentration in 4 mole per dm cube multiplied by the volume, which I need to convert to dm cube by dividing by 1000, and that's because it's cm cube is mole per dm cube, cm cube to dm cube divided by 1000. As I mentioned very early on, candidates should be able to blah 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 blah, conversion between cm cube and dm cube, very very important there. So pop that into the calculator, 4.00 times 20.0 divided by 1000, and I get this one shown on my calculator. But you gotta be careful about what is appropriate number of significant figure. These things are not required in the question, but they are part of your experimental skills in biology, in physics, as well as in chemistry. Look at the data given. 1, hang on, let me choose a different color. 1, 2, and 3 significant figure. 1, 2, and 3 significant figure. 1, 2, and 3 significant figure. Such is the accuracy given by the data in the question. So just because your answer on your calculator doesn't show 3 significant figure, this is only 1 significant figure, because the number in front of the first non-zero whole number, they are just 0, so they do not count as significant figure at all. So to 3 significant figure, it will be 0.0800 mole, and this is just down to your attitude as well as your capability as a science student in order to see the idea of significant figure, what is appropriate, what is sensible based on the data given. Always read the data given and think about it. The next thing, which one is in excess, and I want you to explain. So jumping straight onto what we know from the balance equation, 1 mole of Fe2O3 reacts with 10 mole of KOH. So 1 mole needs 10 mole of these, all right? So if I explain first, so 1 mole of Fe2O3 requires, or needs, requires, or you can say needs, 10 mole of KOH. So 10 mole of KOH. So there are multiple ways of doing it. I'll show you one way of doing it. I'll show you another way. This is 0.0125 mole of Fe2O3. So 0.0125 mole of Fe2O3 would need or would require, whichever word you like to use, just stick with one, 10 times 0.0125, which is 0.125 mole of KOH. But how much I have? I have 0.08, and it's lesser than what I need. So this is lesser than what I need. Therefore, but we only have 0.0800 mole of KOH, mole of KOH, lesser than what is needed, lesser than what is needed. So you know that if you have this much Fe2O3, then you will need this much mole of KOH, but 0.08 is lesser than that. This is what you put in the solution, concentration times volume in dm cube. This gives you the actual mole of KOH you have is lesser than what you need. Therefore, this is completely used up because this is limiting the reactant. They are asking for which one is in the excess, so I can explain it in terms of which one is limiting. So KOH is limiting, and if KOH is limiting, therefore the Fe2O3 is in excess. So what I've done here is I've worked out which one is the limiting reactant and the other one is automatically in excess, and there's one way of looking at it. Alright, so I've just started with Fe2O3. What I could have done is I could have done it another way and it will still be correct. Okay, the same explanation goes to this first line. So I could have said 1 mole of Fe2O3 needs 10 mole of KOH. So I can talk in terms of KOH. So 0.0800 mole of KOH needs, well, this is 10 mole of this require 1 mole of this. So if you have this much mole of it, you need what am I talking about? 0.0800 divided by 10. So I need 0.008 mole of Fe2O3. But how much I actually have? I have 0.0125. So I have 0.0125, but we actually have more. We actually use more Fe2O3 than required. So the one in green is not essential to be included together with the one in pink. They are just an alternative approach to it. Here, I've just explained why the Fe2O3 is in excess, because we use more Fe2O3, 0.0125, whereas we only need 0.008 mole of iron-2O3. Therefore, iron-2O3 is in excess. The one in pink was how I explained it in terms of KOH. With the KOH, we only have 0.0800, but what we need, what 1 mole of Fe2O3 requires is 0.125 mole of KOH. So not enough KOH means KOH is limiting, and therefore the other one is in excess. Two ways to address or to answer these kind of questions involving excess and limiting reactant. Let's have a look at the next example. So we have this equation where we have 1 mole of H2 reacts with 1 mole of Cl2, give you 2 mole of HCl. Okay, so this is 1 mole, this is 1 mole. Alright, so what do we have? We are given the masses of hydrogen, which is H2, the masses of chlorine, which is Cl2. The first thing I would do is I will work out the mole of H2. Given the masses, I shouldn't use volume. Be very careful. Yes, there are gases. Molar volume of gases is 24 dm cube per mole, but this is of gas. It's told to use specifically in the periodic table, so do not confuse mass and reacting volume. So that is divided by 2 because I have the molecule, the hydrogen molecule, the mole of the hydrogen molecule. The MR of H2 is 2 because 1 times 2 for 2 hydrogen. So 2.5 divided by 2, they give you 1.25 mole. And then number 2, the mole of Cl2 is going to be 142 divided by 35.5 multiplied by 2. Because Cl2, each of which is 35.5 times 2 is 71. So 142 divided by 71 is going to give me 2 mole. So from the balance equation, above, 1 mole of H2 reacts with 1 mole of Cl2. So I'm just stating the very obvious thing from the balance equation. So if I have 1.25 mole, so 1.25 mole of H2 would react. So basically, how much would it react with? Because of the 1 mole reacts with 1 mole, so the ratio is exactly 1:1. 1.25 mole of Cl2 will be needed. But what do we have? Okay, what we have is we have 2 mole of Cl2, but we reacted 2 mole of Cl2 more than required, more than 1.25 mole that is required. Because you reacted more than what is required, so very clearly the Cl2 is in excess. So that's how you explain it, okay? You probably don't need to explain, like the whole thing in detail, but you gotta specify which is in excess, and you gotta show calculation to show which is in excess. So that is more than required, so therefore Cl2 is in excess. I have just outlined to you how you can explain it here in terms of the Cl2 being more than required. You could also talk in terms of hydrogen. For example, if you have 2 mole of chlorine, then you will require 2 mole of H2 to react. But you don't have enough H2, you have lesser mole of H2 than 2 mole, and therefore H2 is completely used up. H2 is limiting. If H2 is limiting, then the other reactant Cl2 must be in excess. Be careful about that, yeah? The next bit will be on this reaction, magnesium and acid. So this is metal, reactive metal plus acid, giving metal salt. I told you there are like 5 general equations they've got to master. Without those general equations, every time they throw a new example at you, you will keep on thinking that, it's one example after another, when really it's all about just familiarizing yourself with the general example. The magnesium itself is a solid, it's a metal with a giant metallic structure. This thing is a solution. HCl dissolved in water is HCl aqueous, and you gotta know which one is in excess and use calculations to explain your answer. Just like what we did in the previous question, find the mole of magnesium. Magnesium is an element, it doesn't have an Mr. Instead, what it has is it has Ar because it's a relative atomic mass as given and also as stated in the periodic table very, very clearly for you because you know the periodic table, because you've done periodic table many months ago. So it's 0.24 gram divided by 24 gram per mole. So they give me 0.01 mole. And then number 2, the mole of HCl, the concentration is 2 mole per dm cube. And I got to multiply by the volume, which I then convert to dm cube, so that my mole per dm cube times dm cube will give me mole. That's what I meant by follow the units and you'll be alright. Okay, so what happened then is 2.0 times 5.0 divided by 1000, I get 0.01 mole. So it looks like they are equal, but look at the balance equation. 1 mole of magnesium reacts with 2 mole of acid. So this is how we explain it. From the balance equation, 1 mole of magnesium reacts with 2 mole of HCl. So what do you have? You have, since we have 0.01 mole of magnesium, therefore the mole of HCl required. How much HCl is required? You need 2 times the mole of magnesium from the relationship above. So I am multiplying the mole of magnesium by 2. So I need 0.02 mole. Oops, I don't want that. 0.02 mole of the HCl. But what do I have in reality? I only have 0.01 mole. Okay, but in reality or actual, the actual mole of HCl reacted is 0.01 mole, lesser than required. If you don't have enough of it, it can never be in excess. Therefore, HCl is limiting. HCl is not enough. HCl is completely used up. HCl mole is what you will use for your calculation, but the question specifically asks for which one is in excess. Because HCl is limiting, therefore magnesium is in excess. So there are 2 ways of answering this kind of question. Either you did it the way we did before, where we could see that the CO2 is more than that, whatever is required, the CO2 is in excess. More than required, therefore it's in excess. In this question, just like I did in the very first example earlier, I showed that the HCl is completely used up because sorry, the HCl is not, it's completely used up, because this is more, sorry, this is lesser, I beg your pardon, 0.01 is lesser than whatever you actually requires, and therefore this is completely used up. There isn't enough of it, it's limiting, which means the other one is present in excess and it's not completely used up. Alright, so that's it really in these lecture tutorials, specifically on limiting and excess reactant. I hope they have been useful, and you should go through some of the associated work with it, which I will release tutorial videos going through this particular work in another separate video. Thank you for watching. Follow me at ptet.chemistry on Facebook, Instagram, and Twitter, and don't forget to click the button on the bottom right to subscribe to the channel. Thank you for watching.